Okay, we're ready.
Okay, that looks right.
Yeah, go ahead.
Okay, we're ready. Well, thank you, everyone, for letting me give this talk, and I'm very sorry not to be there with you. I would have really loved it, but I couldn't quite make it. All right, I hope I do a good job. It's 3 o'clock in the morning here, um, but I'm mostly awake, so we'll see how this goes. Um, it's quite a outrageous thing to send the spacecraft to another planet and then or moon and have it land on its surface, and especially when you know so little about that place. Of course, the reason to send the spacecraft to Titan is to learn more about it, learn more about its atmosphere in particular, but the problem is to design the mission, you actually already need to know something about the atmosphere, and so that's kind of the basic problem. And very early in the mission, we had something called a Titan Atmosphere Working Group, which, geez, it went on for maybe 15 years or something like that. That I led most of that time. And I'm going to kind of talk about that a little bit. Could we go to the next view graph? Of course, next one. Skip ahead. Whoops, next one. Sorry, thought I deleted those. It starts with Voyager, which obtains some of our first information about Titan, Titan's atmosphere at any rate. And I'm going to concentrate mostly on the upper atmosphere. And what I'm showing here is some results from Voyager UVS experiment, which did some of the first occultations in the solar system. And in a lot of ways, it was kind of a visionary experiment to think you could send a multi-channel spectrometer to a faraway place and learn about the atmosphere by doing solar ultraviolet experiments. And now we do this a lot more often, and we do it a lot better. So this was sort of an exploratory instrument, you might say. Um, and the data is shown there to the right. Um, and let me see. What I'm trying to say is that if you compare this data, for example, to similar occultations that are done by UVIS, and I hope that gets talked about at this meeting, the data quality of the UVIS measurements will be extraordinarily higher. And that's, of course, because we've learned how to do this better over time. Um, but I'm not trying to denigrate the experiment. It was still, for its time, an extraordinary experiment. So if you look at that plot on the right and you look at it carefully, it's just loaded with artifacts, things that aren't real measurements of the atmosphere, that like artifacts created by the experiment itself, like that big peak at 1200 angstroms, for example. That's not a feature of Titan's atmosphere. Um, Nevertheless, being very brave and there being no other option, these data were analyzed and determined the temperatures there that are listed on the other side of the screen. And there was two experiments, an entrance or two sets of measurements. Going into occultation, the entrance, and that was at the evening terminator, and leaving occultation, that's the exit, that's at the morning terminator. And it gave results which are sort of marginally consistent, um, but do show a difference that probably may or may not be statistically significant. Anyway, the whole point here is that that might not give you the highest confidence in the world that you actually understand what's going on with Titan's atmosphere, but that's all we had. Okay, can we go to the next view graph? And there was a whole bunch of uncertainties. You may remember there was a big question about argon. As noble gas, argon is very hard to measure with remote sensing. And there were theories that the argon abundance on Titan should be quite high. But then it's possible that it was also quite low. So there was a very large range in argon abundances, possible argon abundances. And that affects the CH4 abundance because we had from Voyager measurements of the mean molecular weight of the atmosphere, or inferences of the mean molecular weight of the atmosphere. And you can, but you can balance off argon and CH4 since one's heavier than N2 and the other is lighter than N2. There's various combinations of the argon and CH4 abundance, which would be consistent with the measurements. So you don't know what argon is, and that implies some uncertainty in CH4 and the temperature. And again, we have these two measurements of the temperature in the upper atmosphere that are different and perhaps not as reliable as you would like them to be. So that's another uncertainty. Okay, so the the trajectory of the probe, of course, depends on all these things. There's various things that could happen. The probe could burn up in the atmosphere before it gets to the surface. The probe could have skipped off the atmosphere and gone into, interplanetary space, and lots of things in between, some of which I'll talk about some more. And so it's important to try to pin down these uncertainties, pin down the atmospheres so you have exactly the right trajectory, you enter at the right angle and the right speed to have a successful mission. Now, just the idea of Cassini generated a lot of work even before the spacecraft was built, scientific work. And there was this very interesting paper in 1984 by Yelle and colleagues about the chemistry of the atmosphere, based largely on Voyager results. And I'm showing some of that here. The important point for this talk is the abundance. Well, I think you all know, and I hope there's a lot of talks there about the incredible richness of the chemistry of Titan's atmosphere. In our solar system, it's really by far the richest chemical system we have to study. And so there are these basic constituents like nitrogen, methane, and the photochemistry then creates a sort of vast suite of other constituents. And the one I want to concentrate here is HCN, which you can see on that plot. And the prediction is that it has an extraordinarily high abundance in the upper atmosphere. A few tenths of a percent. And that's going to be important. And over there on the right, it shows some of the chemical networks. Basically you have nitrogen and methane, you break those two apart and recombine the fragments and you can get HCN. And so that's why it's so abundant. Okay, next slide, please. And so this is kind of where I got involved because I realized that HCN was an important coolant in the atmosphere, especially that quite large abundance. Previous to this, there'd been a lot of sort of, we're struggling to understand the temperature of Titan's atmosphere. There was some calculations which gave very high temperatures, turned out to be incorrect. It was hard to understand why the temperature wouldn't be high, why it would be quite so low. So I thought the answer was that there was cooling by this photochemical product, HCN, and I wrote a paper about that in 1991, and here's a plot from that paper, which shows that kind of there's a balance between, this is a very simple calculation, just balances the solar heating rate with the HCN cooling rate, and the two balance if you assume a mole fraction of 10 to the minus 3. the temperature comes out at which the balance occurs comes out to be 187 K. And that's just a very rough calculation, but tells you you're in the ballpark. That's kind of roughly where the temperature of Titan's atmosphere is. And for the mission design, this is reassuring because, as I said, we had two measurements and they were different. One possibility was that the temperature varied greatly over the globe of Titan. For example, the day side could have been a lot hotter than the night side and things like that. And this very strong control by HCN cooling suggests that's not the case, suggests there's some stability there. Okay, so can we go to the next slide, please? All right, so we then put together some engineering models for the atmosphere that were used in the planning for the mission. And there's a number of people involved that are, in addition to myself, Daryl Strobel played a big part, and Emmanuel Lelouch and Danielle Gauthier. And these are shown here. You can see we had sort of a recommended model along with a range of models reflecting all these uncertainties. There's still an uncertainty in the upper atmospheric temperature. There's this uncertainty in the methane mole fraction. A related uncertainty in the argon mole fraction, which for various reasons we thought could go from anywhere from 10% to 0. 0 turned out to be closer to the right answer. It's actually like parts per million, which is scientifically interesting, but means it doesn't have a very big effect on atmospheric thermal structure. And we had lots of constraints, mostly from Voyager. In addition to the Voyager UV occultations, there's the infrared measurements from Voyager Iris experiment, which is sort of a predecessor of Sears, is shown to the right. And of course, if you can turn all these knobs and try to balance the various physical aspects of the atmosphere to still reproduce these measurements, and that gives you this broad range of possible atmospheres which do that, which are shown here. And there's tens of percent uncertainty in the atmospheric temperatures and densities and so on. Okay, so could we see the next view graph? And then there was all kinds of other concerns that sort of came up as we were going along. And I think some of you will remember this. For example, there's a shock in front of the probe as it goes through the atmosphere, and that glows brightly. And there's this band in the UV from the CN molecule, which is created by the thermochemistry in front of the shock. And for a time, we were worried that the radiation from that would adversely affect the heat shield. Maybe the melt glue was holding the heat shield on. And I remember Olivier Vitaska got sent to the laboratory to kind of measure various things about the UV band and the material used in the heat shield. So there was concern with that. There was also concerns with gravity waves in the atmosphere. So gravity waves are just, periodic variations in atmospheric temperature and density, but they can get quite large. And I've never understood why it was designed this way, but to release the parachute on the probe, you have to first turn on the power to the system that releases the parachute, and then you have to give it a signal that says release the parachute. So two things have to happen, and they were controlled by different things. One was controlled by the timing from the probe release into the atmosphere, and the other was controlled by an accelerometer. And it was realized that if there was large enough gravity waves, they would affect the acceleration of the probe, and those two things might not happen in the proper sequence. Fortunately, none of that happened, and and as you know, the mission worked and was spectacularly successful, but it sort of created a lot of worry while we were sitting around waiting for Huygens to get to Titan. Okay, next view graph, please. So here are the results, and this is showing that was the recommended model from those engineering studies with the results from the Hasi probe that got mentioned a minute ago, and so it's actually not too bad. The temperatures are kind of close, even though there's far more structure in the Hasi measurements. And then one thing I wanted to mention is, you know, the temperatures in the stratosphere, they're around 250 kilometers, or maybe more different than we thought they should be. And I still don't think we understand that temperature. So that's for the next mission. Okay, let's go on to the next one. All right. Of course, over the course of the mission, we continued making measurements of the atmospheric structure, and I want to talk about that just a little bit. So these results now, not from Huygens, but from the INMS, the mass spectrometer. Measure the mass spectrometer measures the densities in the atmosphere, and from that, you can infer the temperature. And these are results from a paper by Darcy Snowden, who was a postdoc with me during the Cassini mission. And so on the left paper was maybe 2/3 of the way through the mission, not at the end, so it's not all the data, but a lot of it. In the upper left is shown the coverage of the Titan orbiter, these passes during which we're making measurements from which you could infer temperature. And you can see there's a lot of measurements, but there's a lot of empty spots too. And that's not even all the variables, because there's a time axis too and things like that. So I'd say we had sort of spotty coverage of the atmosphere of Titan. And what we found was there, in fact, are quite large variations in the atmospheric temperature, and you can see some of the results there on the right. The average temperature is about 150 degrees, and but on occasion the temperature can be as cold as maybe 110, 120 degrees, or as hot as 250, 260 degrees. And I wanted to emphasize that. We looked at that data really, really hard. The data is solid. If you look at the upper left corner of the colored plots there, I don't know if you can see my cursor, T41, those are real temperatures, and it happens a number of times, T43. So there are these very large variations in the upper atmospheric temperature on Titan that I don't think we've ever fully understood, and that's really because we didn't have enough sampling. So we need another mission to Titan to understand what's going on there. Down in the lower left is kind of a different presentation. It shows the average temperature profile. That's the black line in the middle, and then the statistical variability is the shaded area. So it's quite a lot of variability. So Titan has a very variable upper atmosphere, and it would be nice someday to understand why. Okay, next view graph. Okay, that's really all that I had to say. As I said, it was kind of an extraordinary thing to send a spacecraft to another body about which you know so little. But that was also tremendously exciting, and it was a real privilege to be working in planetary science during this era. and I hope that the younger generation, okay, I'm old now. Some of you are even older than me, and we lived in an extraordinary time. Because we had all these tremendously exciting missions going to measure things for the first time. And I really hope that the younger generations have similar opportunities, but I'm not really sure about this. So something we have to pay careful attention to, I think. And part of the reason I hope that is that we've only scratched the surface of John Zarnecki's scratched the surface, but metaphorically speaking, we've only really scratched the surface of Titan science. There's a lot of unanswered questions and a lot more things there to investigate. All right, so since I've kind of moved off into the realm of politics, I'll stop there.
Thank you.
Okay, any questions? Roger. Okay, so very quick. Yeah, running out of time.
Right, Larry Esposito, I just want to mention that on TV, just a few weeks before the probe release, we did do a star occultation that was able to check the Yelle model. We stayed up nights to basically confirm that the engineering model would work.